this, that if I have an object that's moving, it traces this path, right? How do we represent the motion of the speed of light? How do we represent light on this graph? And the answer to that is, well, if we know that light travels some 300,000 meters per second, 10 to the power 8, so a few more zeros. Yeah. So if we have light and we know that it travels this much meter in 1 second, we could say that this particular unit is 3 into 10 to the power 8. So that's one line in my grid. 2 lines on my grid would be 6 into 10 to the power 8. 3 would be 9 into 10 to the power 8, right? That's fairly intuitive. What this means is that in 1 second, light gets here. Second, it gets here. Third, it gets here. Fourth, it gets here. Fifth, it gets here. And what this says is that in this particular choice of units, light will always be a 45-degree angle. Is this clear?
So the speed of light is nothing but the angle that you are measuring here. So that's why it remains same, no matter whatever the references that we change. Okay.
Yeah. No, we're not talking about a change of reference right now. I'm saying if I'm standing still, okay, I'm just choosing a coordinate system in which light is at a 45-degree angle. Is this clear? This is an important point. All I'm doing is choosing my units of x so that like the smallest one grid unit is 3 into 10 to the power 8. Which means in 1 second, which is here, my light would have reached here, light would have reached here, light would have reached here. And if I draw it, it means that in this set of coordinates that I'm talking about, right, light is always traveling in a 45-degree angle. Is this clear?
Yes, yeah.
We'll work with the tangent right now in a bit. But what I'm trying to say is that if this is the speed of light, remember what we said earlier. So here, a car that's moving at any other smaller speed, let's say here, is whatever. The speed of the car could be, let's take a Formula 1 car. Okay, that's the speed of the car. We now want to kind of figure out how to transfer and translate our frame of reference so that we bring the car here and then I move myself. Oh, blue is light. So I move myself that same angle here, right? That's what relativity is. That if, for example, if the car sees me at this angle, I should see the car at this angle, right? So there's a fundamental problem right now, which is that if I rotate my coordinate system, what also changes when I rotate one of the angles is the speed of light. And this is the first constraint that we want to be looking at mathematically, that it's very difficult, or it forms a problem where you try to find a way to relate two coordinate systems while keeping one and only one speed the same, whereas every other speed that you have can change. Do you see the problem? See the problem that I want to find a way to rotate my coordinate system, which leaves this 45-degree angle unchanged, but allows me to move all the other, speeds that I have inside this region. And finding such a transformation is difficult, and that's why finding the actual representation of this thing was so important that it was named after the person who discovered it, whose name was Lorentz. And I want to start by showing you a picture, because if I can show you a picture of this Lorenz transformation, it might make it easier for you to understand and appreciate what this is. So if you look at, can everyone see my screen at the moment? Does everyone see this? I've opened up a tab on Chrome and you can see this.
Yes, we can.
So looking at what my graph was earlier, you should now start to see that there's some similarity, that these 45-degree angles that I'm talking about here represent the speed of light, right? That's what these are. This thing is the speed of light. So if you can look at the y-axis, this is just me setting a clock on this particular observer. If you look at the purple dots, that's them moving at a certain speed away from me. Okay, the blue is moving faster, black is moving even faster, green is moving faster, pink is moving even faster. And they're all moving relative to me at this point in time. And what I want to know is, how does any observer, let's say purple, look at the world? And what I need to do is find a way to shift purple onto my frame of reference. And if I do this, note how the 45-degree angle here, this line, which is the speed of light, remains constant. So I just want to show this to you. It's a very nice picture to play with. Do you guys see this? I'm finding a way to transform in between different coordinate systems, but I found a way to do it which leaves the speed of light unchanged. You see?
Yes.
So if I didn't do it this way, the problem would be that I might find a frame of reference in which the speed of light is twice what's actually observed. So that point that the speed of light must be constant regardless of which frame you're looking at. So for example, if I switch to this one and we are the x's, you can tell that this pink dot over here is moving pretty quickly, in one direction. But if I move to the pink observer's frame of reference, I'm moving equally at that speed, but it itself is now moving faster than the speed of light. Do you see this? Right? This, what I have in my screen, is what a Lorenz transformation is. I wanted to show you pictorially what it means before we mathematically look at how we arrive at these transformations, what they mean, how do we constrain these equations, and we're going to derive them shortly. Okay, but I want to point out a few interesting things in this graph before we look at something else. So I just want to point out what the different points in this graph mean. Okay, so I saved a screenshot earlier. Okay, so this is the same picture, nothing different. Can everyone see what's on my screen? Okay, so I want you to notice that essentially what I have and how to read this graph is as follows. The y-axis just tells you how to tick time. So if you look at the line that I'm currently drawing, can everyone see this red mark? That's the point at which my time is 2 seconds. Okay, this is at 3 seconds. This is at 4 seconds. This is at 5 seconds. This is at 6 seconds. Is everyone clear with that? So according to my own frame of reference, I'm standing still. That's the important. The one major takeaway that you have from this graph is that I'm looking at this set of crosses, right? This is me at the frame of reference where I'm at rest. Do you notice how I'm not moving in space? I'm not moving with any velocity, but this is the frame of reference where I'm at rest. That's what a frame of reference is. Okay, so this is how I would measure time. Tick, 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 tick. But to me, everyone else on this graph is moving away with some velocities, right? Is this clear to everyone? So the first thing I want to point out now is look what changes and what we lose when we move across different frames of reference. That was the first question that we started off with. And some of you said that the time changes, the length changes. I'm not even going into the math right now, but I'm going to look at the graph and explain where it comes from, and then we're going to shortly derive these equations. So take a look at this. This line that I have here, okay? This line that I draw happens at one slice of time, which for me is at 1.5 seconds. Why? Because this is at 1 second, this is at 2 seconds, right? Is everyone clear? Which is to say that everything on this line happens when my clock hits 1.5 seconds. Can everyone say okay if they've got it?
Yeah.
Yeah. So
Yeah, we
here's
got
the
it.
first thing
Yes.
that's really crucial. Okay. This is the first thing I'm going to show you that's really crucial. So if you can look and see to me, if I'm the cross right now, right? This event, let's think of these. What are these dots that you see? You can think of them as flashes of light. Like at 2 seconds, a light bulb goes flash, 4 seconds, flash, 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 right? That's all I'm doing. I'm just counting down flashes of light. Note something that's of interest here. Can you everyone look at this point here? Okay, I can zoom in if you'd like. Can you see that this purple spot and this pink spot happen at the same time t is equal to 4 seconds? They're all on this line, right? So for me, if you can see, this green thing is in the future. It's happening at some 4.5 seconds. This blue thing is also happening at around 4.5 seconds. Is that clear to everyone? Only these two, the pink and the purple things are happening at 4 seconds. Is this clear?
Yes.
What I wanted to show you now is the first thing that changes when we change a frame of reference. So what we're going to do with the Lorenz transformation is essentially move, right? We're going to move across. Hang on, I've lost. No, it's not what I wanted. Full screen. Yeah. So now note, if I move a frame of reference, all I'm trying to do is slide it so that the object that I'm studying, either the purple thing or the blue thing or the green or the black, falls on my y-axis. That's all I'm doing. Do you notice? Yeah, that's my frame of reference. I'm changing to an observer that's moving relative to me. So I want you to note where my mouse is right now. This event that's a pink and purple happened at the same time for me at 4 seconds. And now I'm going to ask you is how does the green observer see these two events? Can everyone see this? The pink one and the purple one. Have both of you got it? Have all of you got it?
Yes. Yeah.
So now if I ask the question, how does the green observer look at these events? Now let's look at the 4 second mark. Can everyone see what were the 2 points that we said happen at the same event in time? The purple and the pink.
The purple and the pink, yeah.
But now look what this graph is showing us. This graph is telling us that if you move to how the green observer sees the world, purple happens first at 4.2222 seconds. Then you have the cross at 4.44 seconds. And then you see the flash of light from pink at 4.6 seconds, which is an astounding observation when mathematically they first described this. They said that the first thing you give up when you move across different frames of reference is that objects or events that were simultaneous. Like if you're standing here and you see a flash of lightning or like a firecracker explode at the same time, to some other observer, it may not happen at the same time. Can everyone see this in the graph right now? We're seeing it for ourselves. I've lost my...
Yes.
Yeah, can everyone see it? So if I move back to this cross now, you can see it's relatively all are happening at 4 seconds, right? The pink is happening at 4.02. All the things are mostly simultaneous. But if I move to a different observer, objects and events that used to happen at the same event in time don't happen ever at that event in time. That's the first observation that I'd like to make. Okay, now how do I get rid of these dots? 1 second. Okay, the other thing, reset the map. The second thing, which I'm not going to derive yet, we're going to do it mathematically, is to note that how time may tick differently for different observers. And for this, I think I'm just going to go back to my Discord. Yeah, can everyone see my notebook again?
Yes, yeah.
Yeah. So the other thing, and you may have heard of this, is time dilation, right? Like the idea that different observers see events happening at different times. The first thing we've already seen so far is that we lose simultaneity, right? The second thing that we note is that, and something that takes me 4 seconds. Can you see this? 4 seconds for this orange tick. Does everyone agree that this orange tick, flash of light, whatever you want to call it, happens at 4 seconds, right? If I move back to my globe now, this event that happened at 4 seconds, if we ask how it looks from the green perspective, can everyone see it's now been shifted to 4.3 seconds. Does anyone notice this? Just if you look at the y coordinate of the point that I've picked out. An event that to me happens when my clock strikes 4, to someone else happens at 4.3. This is essentially what you may have seen in the literature or when you're learning for the first time. This is what time dilation essentially is, that different observers disagree on when certain events occur. Okay, so I want to go back now and let's work on the math. Does anyone have any questions so far? As far as I'm aware, this graph is not taught in schools for some reason, nor is it taught in colleges, but it's fairly useful to understand and think about what a Lorenz transformation is. And I just want to show you again, the biggest takeaway that you want to take from this is that the speed of light, which is the 45-degree angle, doesn't change. But if that's the constraint that we put on the world, it means that we give up the idea that there's a universal time. We find that different observers, when they change our frame of reference, that's all we're asking. The question I'm asking you with the graph right now is, what changes when I move from one frame of reference to the other? There's a list of things that change now. Events that were simultaneous and happened at the same time no longer happen at that instance. you find the time intervals. If I said like the time between me setting a stopwatch and me stopping it is 4 seconds, to someone else it might look like 8 seconds or 9 seconds. So just to reiterate that point, 4 seconds for me, which is here. Can everyone see my mouse where it is? If I was looking at an observer that's moving really, really quickly, right? To them, that 4 seconds gets stretched out even more and more. So this is where we're at. It's almost 8 seconds. So the faster you go and the faster you get to the speed of light, the slower time looks. And we're going to describe this mathematically soon. But you see this? This is essentially how we understand how speeds work. Does anyone have any questions before we now derive the Lorentz transformations and the mathematical formulation for this?
I think we can move on to the more questions from my side. Maybe others might have.
Has anyone seen this before? Like, I don't want to waste my time if you guys have seen this graph before. To me, it was fairly new. Like, I didn't learn this. It wasn't taught to me. But I'm hoping that this is something that you see as profound, that events that were simultaneous aren't simultaneous anymore.
It's totally new for us, so we can go on here.
Okay. So no questions. That was crystal clear to everyone.
Okay, I just have one question.
Sure.
Okay, so here we have considered the speed of light to be that the factor which causes this 45-degree angle. Like we have considered the speed of light to be the reference. What if we take some other velocity reference and go on? So there, this whole thing differs in a different way, right?
Yeah, but the only thing that changes is whatever this new thing is, it may not be a 45-degree angle.
Yeah,
it may not be a 45-degree angle. If you start, it could be something else, maybe 60-degree angle, but that one angle doesn't change when you change reference frames.
Okay, fine. So yeah,
there's nothing special about a 45-degree. Nothing special about it. It's just a convenient choice. And the units.
The one thing which I wanna ask further is that so like if we have different velocities, then the angle which its substance differs. So what made actually people to stick on to that speed of light to be the actual factor that we can stick on to? Yeah.
Because that's the fundamental thing that doesn't change when you change reference frames. Okay, it's the one invariant. So remember this, the question I started by asking is relativity is the study of what changes when you change reference frames. And we saw an example of how time changes. Your conception of ticking, something that looks like 4 seconds to you looks like 4.6 seconds to an observer that's moving quickly, right? We saw that events that are simultaneously, that happen at the same time for you, happen at many different instances. One happens at 3 o'clock, the other happens at 3:05 and 3:10. So the point I'm trying to make is that what changes in our world is time, length, simultaneity, which means any physics that we do better not depend on these concepts. Because if they change depending on the observer that looks at them, our physics is wrong. So we want to be looking at objects that don't change. And the first thing that we got was that it's the speed of light. But to me, this isn't very helpful because this is pretty useless. Like, what do you do? Like, okay, the speed of light doesn't change, but how do you mathematically use that to describe a particular transformation? It's not very useful, is it? Okay, so now we're going to look and try to understand what the Lorentz transformation looks like. Yeah. Sure. Yeah. Yeah. Someone have a phone call. Okay, so here's the idea now. If you remember, we went back to this object that we called a 4 vector. You guys may have seen vectors written like this before. That might be a convenient way. But the reason I'm differentiating between these two is that we're used to thinking about this as like 5i plus 6j plus 7k, right? So whenever you think of this kind of vector, this notation makes you think about a 3 vector, an object in space that's pointing in some way. This thing should not scare you. Essentially, all this tells us is the name of the vector. It could be anything you like. It could be x, it could be a momentum vector, it could be, yeah, those are essentially the 2 ones you use most often. And the index up here is nothing but, it just tells us which coordinate you're talking about. So if I were to say x naught, I just mean ct. If I were to talk about x2, it means y, right? So here's what we're going to do. So the one thing that doesn't change, okay, the speed of light, what we're going to do is we find out that there's another invariant when you look at Lorenz transformations. And the other invariant is that if you have an event here, okay, S, and you have another event here, let's say S prime, while in these, when you change the coordinates, does anyone see? I think my problems with
No,
syncing
no,
again.
it's just stuck at the text in
Yeah.
the second coordinate.
Okay, we're getting to the real like math that I wanted to show you. From here, we can do it on a Jamboard if you have one set up. Otherwise, I don't know why my notebook isn't syncing as quickly as it should. Yeah. I'll work on just getting this to sync again. Sure. I hope this was useful to you guys so far. Like if you've all seen this before, I don't want to waste my time on showing you something that you've already been thinking about. Jamboard's up. Okay, then I can stop sharing my screen, right? If we're looking at a Jamboard. We're not going to be looking at transformations, how you describe them mathematically. Guys, tell me what you've been thinking about so far. Like, do you find this useful? Have you thought about these concepts before?
It's like we were taught about this like in our second, I mean like our second semester, like third semester, when we had like the special relativity and such in mechanics, but like not in this brief though. Like we were given the basic idea, like what happens if we like switch coordinates and if we switch reference frames as such. Yeah. Mm. Yeah.
Yeah, but you see why you need this. It's a
Yeah.
groundbreaking phenomenon because I'm going to get to the important things now. Is everyone on
Yeah.
the
Like this
Jamboard?
is,
I think we
yeah.
see
Yeah.
4 people. You could do that. Okay, let's see how this works. Is everyone on the Jamboard? Is anyone not on it on the chat? Could you just say something?
Yeah, I'll join in 2 minutes in Jambo.
Okay, I think I'll give you a quick aside on abstract algebra. If everyone's on the Jamboard so far. Okay. Is everyone ready? Can everyone see what we're writing? Is anyone left out of the Jamboard right now?
Yeah, I can see it.
Okay, so I want you guys to start thinking about what a transformation is mathematically. Okay, and again, I'm just going to ask you guys to think about this. If I had a coordinate system or any coordinate, there are a lot of things that I could do to this and change it. Okay, so the first thing I could do would be I could rotate it. And we've kind of looked at this before, but if I rotate it, how does it look? Well, you now have a new coordinate system that's here, like this, right? How do I describe this? And I'm going to do a quick aside into linear algebra and why we need matrices. But can anyone tell me what essentially a matrix is? And what does it mean for it to be? What do these numbers really mean? Does anyone know? Like, I know everyone's been taught this, but
It's
I'm
just
trying
like
to
an
make it.
arrangement of your numbers in like in rows and columns, or like in a spatial arrangement.
It's an arrangement of numbers. Does anyone else have a definition for what a matrix is? Does anyone agree that that's what we call a matrix?
So the arrangements are made in such way that it has information about certain stuff when expressed in other ways and all.
What
So it's a
information?
form of like for example, a vector can be a vector or a quadratic equation can be expressed as matrix.
Sure.
So in that way.
Anyone else? Does anyone else have any idea what essentially this is? We've all learned them as a collection of numbers. And that's the biggest travesty of justice in mathematics that I've come across so far. Anyone? Does anyone have any other definition of what a matrix is? Okay. Transformation. Okay. Pugal has watched videos on YouTube. Does anyone else agree with Pugal's definition? It's a transformation. Is this new to you? This one concept I need you guys to speak up about. Out of 1, 2, and 3, which definition of a matrix is most familiar to you? Pratibha and Rachna, if you guys could also speak up, please. Anyone? No? Are you guys there, at least?
Yeah, number 1 is the most familiar.
Okay. Pratibha? Is Rachna?
Yeah, like I can understand what he was talking about for the second one, but third one.
Okay. Yeah. So for the third one is something that's interesting to think about, and I'll explain why that is. So, I mean, depending on if you're a mathematician or something else, you look at a matrix differently. But the truth of what a matrix essentially is this going from a coordinate system where, how do you define a coordinate system? Well, you have something called a basis vector, which we call I hat, and another basis vector here that we call j hat, right? Essentially, what a matrix does, any matrix, A is A, B, C, D, right? What a matrix does when you act upon this on any other matrix, right? What it really is you transforming one coordinate system to another. And every time you look at a matrix from now on, you want to be thinking about what this really means. So let's go over a quick few examples because this is really important and hopefully it'll change your lives. Because I'm going to ask you one last question, which I want everyone but Pugal to answer, right? Which is that if a matrix is an arrangement of numbers, right? Or if it contains some information, I'm going to ask you 2 questions that I want you to explain to me. One, what is the inverse? What is the inverse of a collection of numbers? Like, what does it mean? And what really is the determinant?
Like you want what's the inverse of the matrix? Like
I
what?
don't want a formula. I don't want a
Not the
formula, but
formula.
I want to
Like
know what an inverse means.
inverse of a matrix is like another matrix, which is when multiplied with the original matrix give a unity, like a what's it, a unity matrix. Like
Okay,
you want
but
yeah.
why do you have an inverse if it's a number? Like, what does it mean? Like, an inverse means it's the opposite of something, right? So why can a collection of numbers have an opposite?
I didn't quite understand. Once can you repeat the question?
Inverse, by the
Yeah.
definition of what an inverse means, is that, for example, if I have z, a number, an inverse would be 1 over z. That's something that, as
Hmm.
you said, if you multiply 2, it cancels out, right?
Hmm.
But my question is, inverse, by the name and the definition of what inverse means, it tells you it's the opposite of something.
Hmm.
It undoes, like it's an undo button, right?
Hmm.
So my question is, if you have a collection of numbers like 1, 2, 3, 4, what meaning could an inverse possibly have? Like, isn't it nonsense? Like, if I ask you what's the inverse of a banana, you could say, well, it's 1 over banana, but that doesn't that's a nonsensical answer, right? So
Hmm.
what would it really mean? Why can an object like a 1, 2, 3, 4 have an inverse? Can someone explain? All of you that I'm not blaming you. I'm not blaming anyone saying, you haven't understood matrices or not. I'm just saying this is how we were taught. And this is a fair question to ask. Can anyone answer? Apurva?
So if you ask me what is inverse is, then what I would answer is that it's the total, like expressing it in a totally different way, like in a new dimensions that is totally opposite to the initial dimensions that you are measuring. Okay, but
No.
I'm
One
pretty
second. I
sure
want the
about.
other people. Wait, I want the other people who haven't participated yet too. Either Shalik.
Okay.
Shalik said something. So what about Ashmi or Apurva?
I'm not sure, but if we consider like first column as some x-axis, y-axis, it may be like x-axis is going to y and y is going to x. Maybe I'm not sure.
Apurva? I don't mean to put you on the spot. I'm just trying to understand what everyone's thinking at the moment. It's okay if it's the wrong answer. It's okay if it's the right answer. I don't care about if it's wrong or right. I just want to know what you're thinking at the moment.
I do not really know.
Sorry?
I do not know.
You don't know. Okay, no problem.
I don't
That's
have any
okay.
idea.
Pooja, who isn't Pooja, or Pooja, who is Pooja? Pooja is Rachna, right? Rachna and Pratibha. What about you guys?
So I'm not sure if I'm correct. What I was is like, suppose you change the perspective, like and you rotate it to gain a new perspective, something like it's like in verse of a matrix is a new way of looking.
Okay, so we're going to change how you look at matrices from now on, right? What a matrix essentially tells you is all it does is it encodes when I'm going from a coordinate system like this to a coordinate system like this, for example. All a matrix does is it tells me if I know what the basis is in one coordinate system. Meaning, for example, my basis vector here, what would I call it? Oh, well, this is, what's the coordinate system? This, well, it's 1, 0, right? And this one is 0, 1, right? That would be the coordinates of these I hat and j hat, right? All a matrix does is it tells me where on my new coordinate system does I hat and j hat land. So if I was going from this to the blue one, well, you can see, let me make it bigger. Okay, second answer is right. Can everyone see what I'm drawing? Can everyone see this? Yeah. Well, if you look at the unit matrix for this blue thing here, you can see that it lands on the position 1, 1, right? And if you look at the y-axis for this, sorry, the x-axis for this blue thing, it lands at 1, -1. So essentially all a matrix does, okay, is you write it as a column vector where the first two entries tell me where the new x-axis is, and the second two entries tell me where the y-axis is. So matrix now is just 1 and minus 1, 1 and 1. And what does this do? Well, when you have a matrix of any kind, okay, and it acts on your x and y coordinates, which would be, let's say, I'm describing an object here, labeled by, what is it? 1, 2, 3, 4, 5. So x is 5, y is 1, 2, 3, 4. Right? All this matrix does is it tells me in your new perspective, this new perspective, this one, right? What does this x look like? And the way you do it mathematically is therefore take this new one that we got, where this is my new, this is just telling me where my x-axis has landed. This is telling me where my y-axis has landed. And I do this on x and y, which was what? Well, it's 1, 1 minus 1, 1 times 5 and 4. And what this tells me is if we do whatever we learned in school was the matrix formula, it would be 5 plus 4 minus 5 plus 4, which is 9, 1. And this is a prediction I've made now. I've predicted that in my new coordinate system labeled by blue, okay, labeled by blue, this point that I had here should be at 9, 1. And if you do that, you'll find that I may have mixed up the two, but you'll find that the new coordinate system is this spits out the values of the coordinates in the new coordinate system that you've moved to. So that's what a matrix is. A matrix is the way of encoding a transformation from this to this and understanding an object that it says is at 5, 4. You now know that same object is at 9, 1 or whatever, right? That's essentially what a matrix does. What is the inverse? Well, now you can immediately see that the inverse takes you back and says, well, if this is the transformation that took you from this to this is the transformation that takes you from this back to this. That's what an inverse is. And this is essentially what a matrix does. So you can now start to understand what it means for an inverse to exist. Is everyone clear on this so far? This is a fairly important point to make.
Yeah.
Quick test mathematically. What would it mean for me to not change it? What would it mean for me to take a system and not change it at all? Well, if I started with this, I'd end up with this, right? Well, what are my basis vectors here? Well, it's 1, 0. And the basis vectors here are 0, 1. And in the new coordinate system, what is it? 1, 0, 0, 1. Which means the matrix transformation that encodes me going from here to here is labeled by, this one goes here. So that's 1, 0. And this one goes here. Does this matrix look familiar to you? It's the identity, right?
It's the identity matrix.
This is the matrix that encodes me doing nothing at all. Is this clear to you guys? I think it's a fun concept that takes matrices from being these abstract mathematical objects that just contain numbers to you seeing that, oh, this actually means that the basis vector to me lands at what I call 1, 3. And this says, oh, the basis vector that I call y hat now lands at 2, 4. And this is my new coordinate system. Is this clear to everyone?
Yeah.
So this is essentially what matrices are. And the reason I brought this up is because, well, when you move from one coordinate system to the other, we said we need to find a matrix that does this, that leaves the speed of light unchanged. And that's what we're going to do now. Okay? Is everyone clear? Does anyone have any questions?
So this determinant actually means like something which doesn't change across even if you transform stuff.
Now, the determinant has a special meaning, but I'm going to ask you another question, guys. I want all of you to think about this. Okay? So remember, what we said is if I go from a one coordinate system to another, which to me just looks like it's rotated. You understand, like my drawing is pretty terrible here, but what I'm trying to say is that what was my straight line, now I've shifted it like this, right? So I've gone from like that. And what would a inverse transformation look like? Well, it goes to that. Okay. Can anyone now, with this picture, the question I'm going to ask all of you, it's an open question, is what does it mean when a matrix does not have an inverse? This is an interesting question, right?
Maybe doesn't it not come to its initial position.
Sorry?
Like you cannot like like transfer it to another coordinate system, or like you can't like change the coordinate system for that specific values or that specific coordinate.
Maybe, but that's a dangerous coordinate then. Remember, we said that all of our physics must be, we should be able to express it in a different coordinate system. There shouldn't be any preferred coordinate system. And yeah, this is a problem. If we have a matrix that isn't invertible, it means we've taken a point that's here and we've essentially rotated our coordinate system to gone somewhere, but now it's missing. Because wherever it's gone, well, we can't bring it back. And the answer to this, I hope all of you have thought about it, but the answer to an inverse not existing is that it's a coordinate transformation that starts with a well-defined coordinate system. And then, for example, it could take a point here, okay, and it takes that point to 0. And you have another point here that takes another point to 0. So now you have a new coordinate system where in this new coordinate system you have 2 points. I mean, you have 0, which came from 2 points in your old coordinate system, but you don't know which one it came from. This is what it means when you don't have an inverse.
I like it. I was told it was called a singular matrix. So.
Yeah, so that's what it means. This is a singularity, right? A determinant is a related idea. A determinant is something that when you change, I have to draw a grid. I hate drawing grids. A determinant is something that if you have a coordinate system like this, I just drawn different. How is this a coordinate system? Well, this could be this could be my origin, for example. This could be the line y is equal to 1, y is equal to 2, y is equal to 3, blah, blah, blah. And if I find a matrix that takes this and stretches out, can you see how my grid lines are now not the same spacing as they were before? They're just wider. Does anyone see this? That's what it means when the determinant is greater than 1. The determinant is just a measure of how much area you have enclosed in your square, essentially. That's what a determinant is. So if a determinant equals 1, what it tells you is that if you had grid lines that were spaced like this, after your transformation, your grid lines are equally spaced at that same interval. Okay? And now, immediately, that tells you when your determinant is 0, it means that there were grid lines that were well spaced that have now come together to a point.
Okay, yeah.
Does everyone see this? Apurva, Rachna, Pratibha, everyone else who hasn't responded, do you guys see this? This is important. This is an example of a matrix whose determinant is 0. This is the example of determinant 1. This is the example when it's greater than 1, that the area enclosed by like an I hat and a j hat is larger. This is when it's the same. And this is when it's 0. So what this means is essentially there may be multiple points here. Okay, but you don't know where they've come from, which means there's no inverse. So now you can immediately see why for an inverse to exist, it needs to have a determinant. Does this make sense to everyone?
Yeah.
Okay, so let's now start to understand. So we know this now, which means that if you're looking at a Lorentz transformation, okay, we're looking for a transformation that takes our coordinate system, if you remember the space-time globe, it's something within this region, right? Is this clear to everyone? Does everyone remember this graph? We saw this for ourselves. It's linked. You guys can see for yourself. So we need a way for us to move in between these different observers while making sure that this remains unchanged and this remains unchanged. That's the goal. So we're looking for mathematically, how do you express this? Here's the expression, guys. So we knew by now, that x mu is something that has 4 different numbers. If you put mu is equal to 0, well, that means it's x naught. What does x naught mean? It's time. From now on, I'm just going to take c equals 1, which means we're working in the coordinate system where it's at right angles. So we're lazy people. We don't want to keep expressing it again and again. So now if I drop the c, it's secretly there, right? If I take mu is equal to 2, well, it's x2, which is y. Mu equal 3. Yeah. Is everyone clear with this? Is everyone clear with my 4 vector notation?
Yeah.
Okay. So now here's the interesting thing. The interesting thing that we want to do is that if we build any theory, okay, if I have a vector that's in one direction, you might find that when you change your coordinate system to something else, like, sure, it'll be pointing in another direction, but it might be tiny. Something that was a large vector may now be something that's small. Or equally, if you move along that Lorenz transformation graph that you saw earlier, you could have a tiny vector that's pointed higher up. Okay, so the idea is that any vector, okay, changes when you have a transformation. It could be scaled up, it could be shortened down, okay, but it remains a vector. So we need a way to describe how you look at it in the new coordinate system versus the old one. And here's the notation mathematically. Okay, we're now going to get to the good stuff. The notation and what we're going to search for is, I'm going to denote the new coordinate system by a prime. And whenever you see this, I want you to be thinking about this new coordinate system, which, if you remember our axes, it means that you've now moved to an observer, which is now counting the ticks along its own world line. And the old coordinate system, I want you to think about as some other set of points that are somewhere here. And when we move between them, we're essentially moving across reference frames that shift this way. And ask ourselves, how does your tick marks look in each other's perspective? Is this clear to everyone? These are both the same picture, just under 2 observers. So this I can say is x mu, and it counts my blue observer. And the new coordinate system, x prime, counts how what does the blue observer see according to the way I look at the world. Yeah, is everyone clear with the terminology? Is this different for different people? Is everyone clear?
Yeah.
Okay, the first equation we're going to write down is that this new coordinate system is some matrix. I'm going to use this, some matrix times my old coordinate system. Is this clear? From everything that we discussed so far, we know that going between 2 coordinate systems implies matrix. If you're smart and you're thinking ahead, you'll be realizing that it's not just a matrix, but we're going to be constraining this matrix to require that it has an inverse, which means it has a determinant. That's how we do this mathematically, that you could start with many matrices. With a matrix set, you might find a smaller one which has inverses. Out of those, you might find another smaller subset that has a particular determinant. Do you want determinant 1? Do you want determinant 2? Do you want determinant 0? And if you cancel and say, no, I don't want these, you're essentially narrowing and narrowing and narrowing the set of functions that you're looking for that suit your purpose. Does this make sense? Was this a difficult statement to make? Is everyone clear? I'd really like, this is now the good stuff, and this is where we're going to finish the lecture with this Lorentz group. So if you guys have any questions with anything that we've discussed so far, what I'm saying right now, this is the time to say it.
Will the transformation where we have the determinant, will it always be a square, like as you drew in the previous thing?
We've not made any constraints right now, but what I've tried to say is those are the kind of questions you want to be asking yourself. Like, The moment, so the first, all I've said so far is that your new coordinate system is a matrix times your old coordinate system. Okay, that's the first thing. The hidden assumptions to this, the assumption we're making is that the transformation is linear. And what that means and what this encodes is that if I'm traveling with a certain velocity v, to the observer that's traveling at the velocity v, he sees me as going with the velocity minus v, or she sees me with the velocity minus v. That's essentially what this linear transformation is. Okay, so that's the only assumption, hidden assumption that we're making. But what we've said is that if we have a vector, this is a vector, we can describe this vector by a matrix acting on the old coordinate system. Meaning if I have a vector here, I'm going to apply some transformation that in my new coordinate system tells me, how to read this vector based on I hat and j hat. Okay, that's all this is. Is everyone clear? Now we're going to ask ourselves the question on how to constrain this and essentially derive what a Lorentz transformation is. So the first thing I want you to note is that this contains 4 bits of information. Not only does it have x, but it also has t, x, y, z, right? Which means there are 4 equations here. Do you see it? There are essentially 4 equations. I can ask the question, what's happening? Okay, 3 blue, 1 brown. Yeah. I want you to, whenever you're looking at an equation like this, the questions we're going to ask ourselves are how many equations are we actually looking at? And the number of equations we're looking at is 4. Like what is my time coordinate? Remember, x prime naught is t prime, essentially. What is my x prime? What's my y prime? What's my z prime? Those are the questions you're asking. I'm just simplifying it into one line here and saying this particular left-hand side represents all of these here. So we have 4 equations in the left-hand side, right? So now we're looking for a matrix that's common, and we have 4 quantities on the right-hand side. But now if you remember, a matrix has different elements, right? As we discussed before, which relate to the basis and the basis here. We're just going to do a small trick. Okay, now we're going to get ready for something. Okay. The fundamental equation of relativity tells us how to relate an object in our frame of reference and what doesn't change in the other frame of reference. And the thing that doesn't change, while your time changes, while your lengths change, while simultaneity changes, these all can't be used. What doesn't change is this notion of a space-time interval. Okay, and we define this as follows. We say the space-time interval that we're going to call delta S is c, is there a c squared? Yeah, there's a c squared. C squared times my t prime minus t, okay, minus x1, there's a prime. Yeah, give it like this. Okay, does anyone see the equation? I've written it terribly. But essentially what I've done is I've said that there exists an interval which is really no different from the Pythagorean theorem. What this tells you is this is your spatial distance. It's x2 minus x1 squared, plus y2 minus y1 squared plus z2 minus z1 squared. Does everyone see this? And what this tells us, and what the fundamental equation that we have to start with, is that there's this notion of a space-time interval, which says that while your distances may change from one to the other, what remains the same is the radius, your distance from separation. And that's equivalent to me saying if I had an object here, right, like this, if I rotated my coordinate system to something else, and what that would mean is that my object is like now somewhere here. Does the length of this object change? No, the object has remained the same, but what changes is how we measure it. And so if you wanted to find the length, which may be 5 here, we'd have to measure it along this axis take it like this and say, oh, the length is now the hypotenuse, which is just like, what would it be, like 3 squared plus 4 squared. And we find that it is in fact 5. Okay, so this is something that doesn't change when you move across coordinates. And this particular thing is so important. It's the fundamental equation of relativity. It's called the space-time integral. Have all of you seen this before? Is this new to any of you? Guys?
This thing is actually new.
It's new to you.
Yeah.
Okay, good.
But
Okay.
doesn't it lie on the assumption that everybody is like seeing from the same point? Like it's
No,
with
it doesn't. It
respect to
doesn't.
a point, right? In that
Sorry?
graph. We consider that radius to be constant with respect to a particular point.
No. So I'll show you what it is. Can we go back? Well, can you stream? Can I share my screen again for a second? Sure. I'm going to show this to you right from the Lorenz transformation globe again. Okay, and if you guys have any calculators on your computer or something like that, you can see for yourself. Yeah. Okay, do you guys see it? Does everyone see my globe again, the space-time diagram?
Yeah.
Is everyone on my screen?
Yeah.
Yep.
Okay, so we're going to find out that there's a certain length that's invariant regardless of where we go. And that's the fundamental equation I'm going to try and describe on paper now. But I just want to show you and give you guys an example so that intuitively it makes sense before we write it. So if you look at my point here, which is, let's pick a better number. Let's take 7. Let's take 6. Let's pick this point. Okay. It tells me that for the observer that's marked by the crosses, remember that where I go on this graph just shifts my perspective to any observer. And if you see the flashes aligned with my y-axis, that just tells me I'm looking at time ticking and I've attached a clock to a moving observer. So all I've done is change my frame of reference. That's what we're doing here, right? So what I'm going to do is stop at this x and I'm going to stay with the x observer. And I'm going to see, okay, so the time that's ticking for me is 4 seconds. And I want to know for the green observer, how much time has elapsed. And you can see from the y coordinate here that the time that's elapsed is 4.3 seconds. Can everyone see this? And what I'm going to argue to you is that there exists an invariant length, which is very similar to the Pythagorean theorem, but it's a special Pythagorean theorem that exists for relativity. Okay, so I want you to note something. If you take down the value 4.36, yeah, that's like 4.36, and you find that the distance between that is 1.7. Can anyone take that? Can everyone see the coordinates?
Yeah, we can see the
Yeah.
coordinates.
Okay, so do you see the 1.746 and 4.36?
Huh.
Yeah, so the idea is that if you square 4.36, if you were to look at, how do I draw this? If you were to treat this as a Pythagorean theorem example, you draw a straight line from your origin to this green point that I've labeled, and then kind of form a right angle triangle, right? Where the line from the origin would be like a hypotenuse.
Yeah, if we find the square, like hypotenuse, do you want us
Yeah.
to find it?
We could, because, okay, so you'll see what I'm hinting at. I'm trying to say that the speed of light being constant is essentially a hypotenuse in our world, but you'll see why. All I want you to do in a calculator, if you have one, is to take 4.36 squared, square it, okay? Instead of a Pythagorean theorem that you have in that we used to, instead of adding the sum of the other two sides, we're just going to take the difference. So what we're going to do is take 4.36 squared minus 1.74 squared.
0.3.
Okay, if you can tell me what that value is. 4.36 squared minus 1.74 squared.
It's 16.01.
And take the square root.
Okay, it's around 4.
4. And that immediately tells you that your time, according to that particular, like, this is how you relate that the time that the other person ticks on their watch, where and how fast they're moving to the time that you find. So you can clearly see that there's a invariant right from what we've seen so far. which is similar to the Pythagorean theorem that gives us the time that's elapsed in our coordinate system.
Uh-huh.
You guys see it?
Nice.
We can do the same exercise for another point in this graph. Let's take something crazy like this big one. And I'm going to say that I'm expecting the value to be around 8. Okay, we've got 9.2 squared, if someone can do that.
9.2.
9.2 squared minus 4.6 squared.
It's 8, yeah.
Yeah, when you square it, you get 8, which is exactly the time that we're looking at here. So there is an invariant here, but the invariant isn't something as simple as the time that's elapsed, nor is it the distance between 2 points, but we find that they're closely related to each other. And this is the fundamental quantity that we define as something called a space-time interval. Okay? So that's all we've done so far. And this is the fundamental equation. Where's my Jamboard? Okay, shall we go back to the Jamboard? How do I stop? Okay, we're about ready to wrap up in about 15 minutes because we're now getting to the math we ended. So does everyone see that there's some sort of an invariant quantity which doesn't change? And that is that the time itself doesn't change, the distance between the time changes, the distance between two events changes, but what remains constant is something like the hypotenuse, which is very similar to when we rotate a particular object, the true length of that object doesn't change. And this fact is the fundamental equation of relativity. Okay, so that's what we've done. We've said, is everyone back on the Jamboard?
Yeah.
Yep.
And we can go back to the space-time globe if you want. Does everyone see what I've written down so far?
Yeah, we're following
Yes.
it.
Yeah, yeah.
Yes.
Okay, so what I've written down is what we just saw. And the point I'm trying to make is we only did it for one case. But if you transform to another, I'm just going to try and vaguely draw what we were looking at. Oh, shit. I'm terrible with, there we go. Remember, this is our speed of light, okay? And if you remember, we had tick marks like this. And we found that for some other frame and some other observer, it might be like this. But there is an invariant quantity, which is that if I find the time coordinate squared minus the spatial distance squared, right? This entire quantity, when I take the square root, gives me the time that I'm looking at. And what we didn't do with the graph, but I'm going to leave it to you guys to go in and check, is that for that same time period, if you look at some other observer without moving, if you remember, all of them were in this one line like this. If you go to another observer, you'll find that they'll have some other time. Okay, it'll be some t squared minus x squared. And when you take the square root of this, both of them will point to that same point. Okay, so this equation that we have in front of us is so important. It's called the space-time interval. And this particular thing is something that does not change depending on which observer you go to. It's the biggest invariant that you must write down and circle because it's the biggest thing that all of causality and everything that we're going to be discussing in physics in terms of how objects can affect each other are derived from this quantity. Okay, is everyone with me so far?
Yes, yeah.
Okay, so our goal, if you remember, was to say that the new coordinate system, which, if you want to draw a picture in your head, is just from going from this observer to this observer. Just going between these two, right? We know it's given as some matrix. Should be, yeah, times my old coordinates. Remember, this is just time xyz. And this is time xyz. Is everyone clear? Okay, one bit of mathematical interlude here, which is that this matrix I can't just leave blank as it is. Okay, but there's, do you see this? Do you see this in front of me here? The equation that I've written in a box. It's actually, if I write out the full thing, I'm going to take C as 1. Okay, so take a look at this. If I write it as T2 minus T1, okay, what I'm going to say is that my coordinate system is always at the origin. So I'm just going to take T1 to be 0. Yeah, I think that's fairly easy to just say. I'm just saying my T1 is such that it's always at the origin. So I can take I choose T1 to be 0. Okay, writing out the same equation in a different way. Okay, it's T2 minus T1 squared. There's a minus x2 minus x minus x2 minus x1 squared minus y2 minus y1 squared minus z2 minus z1 squared. Right? Everyone can agree with this? So the first thing I'm going to say is I choose my origin to be such that t is 0, x1 is 0, y1 is 0, z1 is 0. Essentially saying I'm starting my point at the origin. 0, 0. Yeah? So my equation now changes to t square minus x square minus y square minus z square is this invariant quantity that I called here. Yeah? Is everyone clear with this so far? Guys?
Yeah.
Okay.
Follow.
So now check this out. So what I want to do is, remember I told you that I can express my vector and my t's and my x's and y's as this one quantity that's an x. Okay, so what I'm going to do is I'm going to ask, can I write this equation t squared, that's all it is, t squared minus x squared minus y squared minus z squared, can I write it as some form of x? Well, I know it can't just be x, there has to be another x here because I'm looking for x squared, right? How would I represent y in my notation? If you remember, y was x2, and okay, maybe I'll take z because it's an easier, less confusing example. Z is x3. So what would z square be? Well, it'll be x3 squared. Yeah? Is everyone clear on this? T squared would be x naught squared. Yeah?
Following it?
Can you guys understand? Is this clear to everyone?
Yes.
I've just tried to write down, so this equation that I wrote in a box, I've written it out as in its full form. I've chosen my origin to be 0. I've simplified it to be this particular thing. And I've said, can I write this out in this format that we had earlier? And there's a pretty elegant way to do this. Okay, and here it is. Here's the elegant way. It's by saying that if I have some matrix like -1, you would have seen this matrix before. Acting on second t squared. What would this matrix acting on this give me? Well, it would just be minus t squared, minus x squared, minus y squared, minus z squared. Right? Is everyone clear? It's fairly easy. Oh, sorry. This should be plus. Or minus and plus.
It's
Yeah,
minus
right.
and the other gets plus sign.
Sorry?
Yeah, it's the same. Like I said the same thing.
Yeah, you guys are better with it. Okay, yeah. So the way to describe this would be to call this particular metric eta. Okay, and we're going to give it 2 indices. You can give them any, it could be alpha, beta. You could give it rho and sigma. You could give it any kind of complicated Greek index of your choice. The most common is mu and nu. Okay, and you say this same delta S that we had in the first place. Clear this up. The same delta S, I'm going to describe this as eta mu nu. okay, times x mu, And this might seem strange at first to everyone, but all I've done is written the same thing out here. And now I just want to show you a bit of a mathematical convention, which is called Einstein's summation convention, which you guys may have seen, you may not have seen, but it's not a mathematical trick. There's no tricks going on here so far. I'm just trying to stop writing down 4 equations every single time I want to work with relativity. Like I just don't want to write x squared minus y squared minus z squared. It's a pain. I want to write it as, well, this, which is much shorter. But this essentially includes, well, this information here. And what's the Einstein summation convention? It tells you that if you have an index, which is down, and the same index is repeated here, up, you just sum over it. Is this clear? For now, it doesn't matter what I mean by an index down, what I mean by an index above. They're both essentially, for now, let's treat them to be, we're looking for the square of something. Okay, so if I had to write down this object here in its full form, look what it is. Yeah, because anytime there's a index, you sum it across its entire thing, which is essentially saying mu goes from 0 to 3, nu goes from 0 to 3. What does this mean? Well, it goes from t, then x, then y, then z. This goes from t, then x, then y, then z. Okay, now I've changed it to 16 equations. And what I'm going to write down here is essentially, here's what it is. It's 0, 0, 0, 0. Yeah. Does everyone see this? It's almost like a for loop in any kind of coding. But what's interesting to note is that my matrix that I'm talking about has zeros everywhere. Has zeros everywhere except in these places, which is to say that 0, 1 is 0, this is 0, this is 0, this survives. Eta 1, okay, so what is, does everyone follow up till here? What all I've done? I've just not done anything. I've just tried to re-express an equation in a simpler form. So how would you read this? Okay, so what is eta not? It's this thing here, which is minus 1. What's x naught? T. What's x naught? T. So this thing is essentially, yeah, it's minus t squared. Okay. And at this point in time, I just want to show you, if you've seen me mix up my minus t plus x, or whether it's t squared minus x, this is essentially a huge debate in physics. Some people prefer this, some people prefer this. It just comes down to what convention you follow. The first one is usually done in GR. The second is usually done in quantum field theory. So there's no real difference. I've just done it here. It's the same as writing this as +1 minus minus minus. Right? Is everyone clear so far? Is this confusing? All I've done is rewrite this particular term, dropping the c, as here. Plus. Yeah. Sure. Okay, so essentially what, okay, so let me just write that. I'm not going to write the y. Okay, I'll write the y and z. Right? These are the two things that are here. What essentially I mean, the 3 ways to think about it. The first is to say, well, if take s to be 0, can everyone see this? S could have a value, s could also be 0. If s is 0, you've got, right? Does anyone see this? I could take this to one side and I've got a positive thing here and a negative on this side. Or I could take this here and I have a negative and positive. That's one way to think about it. The second way to think about it is it actually has to do with whether you're counting time or whether you're counting and keeping track of distance. Remember that in our world line, this axis of time counts when your clock goes tick, tick, tick. Essentially, either using a minus and plus or using a plus and minuses depends if you're counting this or you're starting to count ticks in this direction. They're equivalent. They're all the same. It's just a question of convention. And you guys will see for yourself later. If you work in a field that has lots of time derivatives, you'll prefer one over the other. If you work in a field that has a lot of spatial derivatives, you'll prefer one over the other. But there's nothing different between the two. All I wanted to tell you so far is I can express this, which is my fundamental quantity. I can express this. Does anyone have any questions so far?
No.
Okay, so if you were confused, what this essentially means is that since all these terms are zero, what would this be? Well, it's 0, 1, 0, 2, 0, 3. This is 1, 0, 1, 1, 1, 2, 3. All these are zero, so essentially you have 4 terms that survive. Okay. Yeah, these are the terms that survive. What is this? This is t squared. What is this? It's minus. What is this? It's x squared. What is this? 1. What is this? It's y squared. What is this? It's 1. Yeah. Does everyone follow? Is this simple to understand?
Yeah.
Okay. So going back now to our Lorentz transformation. We said that the new coordinate system is a matrix times the old coordinate system. And all I'm going to do is say there's one additional factor, which is that the matrix that we're talking about has its own indices. And what does this mean? Just like how if I say eta 1, 1, what this means is that it's, well, in the matrix, it's this element. I mean, not this element. No, 1, 1 is that one. Yeah. Yeah, it's this one. If I talk about 2, 2, well, it's this element here. Yeah, it's just an index that allows me to understand which one I'm talking about. Is this clear? So all I've done is I've said that this Lorentz transformation is a matrix acting on a vector, meaning it's a matrix, and it spits out a new t x, y, z. Is this clear? Is this clear? So remember, our goal is we're trying to find that the transformation that kind of leaves this is the space that we want to work with, but we don't know mathematically yet how to do that. So the question now of mathematically of special relativity is, what the hell is this matrix that we say represents the Lorentz transformation? What is it? What form does it have? How do we find it? And I'm just going to write down one last equation, and I think we can decide if we want to pursue this further today or another day, and so on. Okay, so essentially this is the equation. Okay, so if you notice, let me write this out. You have an input here. The first thing you want to be looking at is that there's a free index on the left hand side, x prime mu, which means it's asking you what coordinate do you want. You could say, well, I want to know what my new time coordinate is, and I can just say, oh, well, mu is 0. Okay, and what this means is that x prime 0, which is t prime, well, in here you want to substitute 0. But remember, I told you this, that whenever you have an index that's repeated bottom and top, you sum. So if you put in the new time coordinate, it's 0 plus is this clear? This is just one equation out of the 4 that you have here. So essentially our goal is to try and understand what this thing is, which essentially gives us this. It'll go on and on. And we're trying to find out what this matrix is. That's our goal right now. Any questions? Is everyone clear on this? This is a fairly important concept.
Yeah.
Have any of you seen this before? Is this familiar to most of you?
New.
No.
Nope.
This is new.
Yeah.
Okay, fine, that's fine. But remember, this thing that you just saw here is the fundamental equation of relativity. It's the one thing you have to be taught. If you're leaving this course and saying, I don't want to learn anymore, the first thing you have to know is that the space-time interval that's invariant is this thing here. Remember what I told you about? This is actually, there's a sum that's encoded between mu and nu's, right? So this is essentially a huge long thing which you can represent as this. That's what this is. Okay. This particular concept here, this thing here, I want to spend a little bit of time. Then we just talk about the Lorentz group a little bit, and then I think I'm not sure how long you guys usually have sessions for, but I don't want to take too much of your time if it's training you or it's getting past the time. So I'm going to wrap up in about 5 or 10 minutes. So I want you to notice something here. If you are working in Euclidean space, right? This does someone have connection problems? Can everyone hear me?
We can hear you.
Yeah, we can hear.
Should keep. Okay. Can you see there's a fundamental
Your
difference between
voice
these
is
two?
breaking a little.
My voice is breaking.
Yeah, it was breaking. Now it's pretty fine.
Okay. So can you see there's a fundamental difference between these two? And this one fact alone tells you the space that you're working with. And I'm going to go back and answer the question about velocities first, and then I'm going to end with the last equation for the day. So can you see this thing? This is nothing but the 4-dimensional identity matrix. If you look at just this small subsection here, you'll notice that that's the identity matrix. You'll find that there's another identity matrix here. So if I had to shorten this, I'd say that's the identity matrix in 4 dimensions. Yeah. And can you see that the metric I spoke about earlier has something that's similar? You have an identity matrix here. But the biggest thing that makes this special is on this side, you have a minus sign. And the minus sign is so important to our relativistic physics that this particular space that we're working on, a space that takes vectors and works with them and transform coordinates, that's what we call Minkowski space. Okay, and this 4-dimensional identity matrix that you saw, that's called Euclidean space. So if you've heard of these words before, today was your first interlude away from Euclidean space to something called Minkowski. Yeah, and I want to talk about something that I want you to go home and think about for a while. Okay, I want you to go home and think about it because it's a subtle concept, right? You could see in our matrices, I'm just going to write the first one. You know that in our matrices, the first column matrix in our thing here essentially tells you where our basis vectors land. Remember, if our basis vectors are here, I hat and j hat, and I transform my coordinate system to something else like this, right? The first set of numbers in a matrix tells me where this new I hat and j hat land, right? That's what this is. So it's actually 1 and minus 1. That was a mistake I made with everything. So look here, this tells you that this is the identity matrix because for you, the first column, which was time, right? Time just lands in a new position that you call time. X goes to X, Y goes to Y, Z goes to Z. And if you had to represent this, you'd say the t, x, y, and z go to t, x, y, and z, which is why you have something called the identity matrix that acts on it, right? Whereas here, right, x goes to x, y goes to y, z goes to z, but time goes to minus time. So that's something interesting I want you to go home and think about, which is to say that if we were finding the square and we have a negative symbol sign here in our fundamental equation, if you remember, this was, yeah, blah, blah. Is there any difference for me saying t goes to imaginary time and squaring it? That's something I want you to just go home and think about, because what does it really mean mathematically? It seems like rubbish, but gives us the results that we see in special relativity. Yeah, just think about that. That's all I want you to do. There are no right answers, there are no exercises, but just it's an interesting point to make. Okay, let's finally get down to the fundamental equation of the Lorentz group. So if you remember, what we just did now was to say that we have, this is the last equation I'm doing. Can you guys tell me, like, are you tired? This has been a long session already. I don't know about you, how long your sessions usually go on for.
Actually, I don't mind like attending for another couple of hours. Like,
I tried to finish in about 10
Yeah.
minutes, and I just want to write down one last equation. So remember, the starting thing that we started with was this. I'm going to keep writing it because it's important to keep writing down, right? And remember this, when you think about it, it says it's something called Minkowski space. Okay, so I wanted to show you something that, so I want to do two last things for today. The first is to ask you about the question with the bullet. If I'm traveling at 8 times, like almost the speed of light, and I fire a bullet that's also going at that speed, does it really result in this or not? That's the first question I'm going to answer. And the second thing is, how do you constrain what this is? So just in terms of equations, these are the two last things we're going to do today. And the first thing I want to tell you is that when you answer the first question in terms of how I can add, we take it as 0.8 c plus 0.8 c, and we say the velocity is, well, 1.6. The problem isn't about, the problem doesn't come with the speed of light changing or these numbers changing, but the abstract algebra that like holds together all the things that we're talking about is that the way you add two velocities changes. And I wanted to say that this is something that we take granted. And this is what I started off this talk by saying, that, you know, trying to prove 3 + 2 = 5 is actually harder than you think it is, right? Because you have to define what this plus is. I wanted to give you an example of where you've come across two different definitions of what a plus is, but never really thought about it. And the first is to say, if I have 3 + 2 = 5, okay, leave aside what these are, my plus tells me that I take an input. I take some number x, I take another input y, and I define x plus y as, well, the mathematical definition is there's something called a successor function, which takes, let's say, 1 to 2, and I apply this y times on x. Okay, that's kind of how addition is defined, but that's not important for us right now. But essentially, that's what we're doing with addition. We're taking an input of two numbers, and we're getting something at the end of it, which also belongs to the series of numbers, whole numbers, natural numbers, whatever they are. But if you take another equation, for example, where I take 3 + 4 + 7 / 6, and I ask you to give me the result, immediately now, when I've asked you to think about what an addition is, you'll notice that the earlier operation, which said, well, you take an input and you give me some kind of output, doesn't work, because now you have to work with these denominators. You guys see immediately, like if you were tasked with coding what addition is, you see that this is different. You have to now, I mean, we had some rule with an LCM to work that out, right? Do you see how the addition operator itself is different? And the way we learned this was to say that, well, this new addition, let's call this addition new, takes inputs which are, let's say, u divided by x, v divided by y, and it outputs it to uy plus vx divided by xy. But you see how this new addition symbol is far different from our old addition symbol, which just took one input, a second input, and gave me x plus y, whatever that was, right? You see how it's different, but we take this for granted. And the idea I want to tell you mathematically is that whenever you look at like an equation like this, whenever you look at an equation like, let's say, 3 plus 2, you say that 3 belongs to a set of numbers which belong to, let's say, natural numbers for now. 2 also belongs to natural numbers. It could belong to other things, but this plus is defined on the space of natural numbers. Same way, when you have 3 by 4 plus 7 by 6, this doesn't belong to a natural number anymore. It belongs to the, well, rational numbers. I forgot. I think it's a Z. I forgot the letter. I think it's Q. Is it Q? Something else. This also belongs to the rational numbers, and the plus now is defined in the space of all rational numbers, right? So now is where you think about this, that the plus, when you're talking about in school, when you learned that there's a boat in water, and if the water is going at 5 meters per second and the boat is going at 10 meters per second, well, this plus is defined in some sort of world in which I could add, just like 3 plus 2, I could naively add 10 plus 5. But we find that this doesn't really work. We need a different kind of addition when we are talking about this. And this addition is what I want to talk about.
So
And the
can I
relativistic.
clarify one part in
Sure.
this?
Sure.
So like we are talking in terms of an observer who's observing the man running at 0.5 times the speed of
Yeah,
light.
exactly,
And
exactly. Good.
not
Yeah.
the
So
man
I'm at,
who's shooting. We're not
no.
talking about
I'm at
the man.
rest. I'm at rest. I'm standing in one place. Relative to me is, if you remember the way we do our diagrams now, relative to me is there's a guy here.
Hmm.
Relative to him, there's an additional sort
Gun.
of
Okay.
gun, but it's not, and it can't be the speed of light. So it has to be less.
Hmm.
Right? So we're trying to ask, what does this work? Or what's the speed of that gun?
Okay.
Okay, so let's do it. So let's say that relative to me, there's a guy who's going at a speed u, which is here 0.8, and he shoots a gun that's going at speed v. Right? How do I add these two together? And the law is that you take u, you add them together with a plus, which is the same old plus that we worked at before. You have a v. There's actually a denominator that's hidden from view. The denominator says there's a 1 plus u times v divided by c squared. And this is the rule for plus. That's defined on what space? Well, earlier we saw that 3 plus 4 plus 7 by 6 is defined on the space of rational numbers. This is how you define a plus on the space that we call Minkowski. It's the space at which, just like how you had a space of rational numbers or learned how to divide and add fractions, all of relativity, all of special relativity happens on Minkowski space. If you leave the space and go to other, fun, interesting things, that's general relativity. But as long as you stay in this special one particular space, that's Minkowski space, that's special relativity. So do you guys see now that you have a rule for addition? Let's work this out. So hang on, let's take the case where u, which is the guy's speed. Remember, so if I'm here, there's a guy who's going at a certain speed, and he's firing a bullet that's going at a certain speed. So this is at u, that's at v. Is this clear? So let's say u is very, very small, and let's say v is very, very small, or even smaller than the speed of light. What happens? Let's look at this fraction. What happens here? So let's say u is 5. Let's say v is 10. You have 5 times 10, 50 divided by how many zeros? What happens to this fraction? Anyone? What's 50 divided by?
Like
It's roughly
we can
0, right?
have next.
It's negligent. So I mean,
Yeah.
it's negligible, which means if this is almost 0, well, I can
So your
erase it
denominator
and
stays
say
one.
denominator is just 1. I don't want to erase this because I'm going to need it soon. But if the denominator is just 1, what this means is that what happens to the numerator if the denominator is just 1? Well, when the speeds are small, when u and v are small, I can naively just add them together. Do you see? Do you see how when the velocities are small, I can just add 5 plus 10? That's what the numerator is telling us.
Yeah.
Yeah. What happens now when u is, let's say, 0.5 V is also 0.5. You have to plug it into this, and you see that 0.5 plus 0.5 divided by 1 plus 0.5, 0.5 by 1. So you get half. So a new velocity, if you fire half and another half, is actually still 1 plus
We're taking it like U is 0.5 times C. Oh, okay.
CC. Yeah. You can work this out. The last case we can take is what happens if you travel at the speed of light, U is C, and you fire a gun which is also going at the speed of light. And remember, our postulate from special relativity was that the speed of light is always constant regardless of how fast you're traveling, right? So we should now get C plus C divided by 1 plus C squared, C squared. What do you get? You get 2C divided by 2.
So it's C.
Yeah, there you go. So this rule of addition now, the one we've defined, it answers our earlier question. It tells us that what we were doing wrong was assuming a law of addition that really doesn't hold in the space that we're considering. And instead we have to change what we mean by addition. And when we do that, the world works perfectly, which is to say that non-relativistic mechanics tells you that you can ignore the denominator, treat it as 1, and just naively add your speeds. When you go faster and faster and faster, it changes the emergent velocity. And no matter how fast you go, when U is C, V is C, the resultant speed will always be the speed of light. Nice, right? Fully consistent. And this is how you make predictions. You make a prediction based off of an equation that tells you, and you make an inference based off of that. Cool?
But like, how do we arrive at that 1 plus UV by C squared?
Yeah, so that's a law that we can do later and arrive at. So, I mean, the questions for the future would be, where did I get that from?
That's like the 1 plus beta squared term or something.
Yeah, it's close. It's related to that.
Okay.
This is just an example. So, I mean, the questions you can always ask me is, how did you get that? The point I'm trying to say is that the answers I give you shouldn't be answers in words, but they should be answers that I can write down in equations. Okay. So I think maybe next time we should look at what this Lorenz transformation is, because I think today we're out of time and it's gone on for quite a while. Can anyone summarize what we've learned so far today? Let's go point by point. Like, what do you think the biggest takeaway was for each of them?
One of the invariant stuff is the space-time interval.
Okay. Someone else? What else did you pick up?
So like the time an event happens changes when the observer and the time frame of reference changes.
What changes? Sorry.
The time at which an interval happens, so the position at which an object is at a particular time changes when the frame of reference changes.
Okay.
Time set.
Anything else?
And what matrix really means? Just not a representation of numbers.
Sorry?
What matrix really means, like what matrix information. Simple, but we didn't like learn it the way.
Then Minkowski space.
Okay. Is there anything else? Okay. Cool. Fair enough. In the future, I'll tell you what the next, what do you say? Next time, what are we going to look at? We're going to see that the fundamental equation of this, whatever we call the Lorenz transformation, which, if you remember, is restricted to the transformations that leave the speed of light invariant. Okay, and we'll find out that the fundamental equation of this thing looks like this. And this alone is all we need to understand how to translate why it leaves behind things and understand this, and understand the matrix better. This is the equation we're going to look at next time. The second thing we're going to look at next time is so far you realize this, right? Like, you realize that if I'm here, okay, if I'm here, this is me, and this is light, okay? What does it mean for an object that's here on this side of it? What about all of the stuff in the world that's outside of this light ray? And we're going to find out that the biggest consequence of relativity is that everything on this side is causally disconnected, which means it's a very interesting fact that you can take away immediately, given that the faster you go, the closer you get to the speed of light. You can't ever exceed the speed of light. So the closest that you could ever reach is touching this point here. Just like if you remember the diagram that we looked at on the globe, right? You can slide along wherever you are here, but you can never cross to this side. And what that tells you is that there's a region in the universe far away from us where light can never reach us from there. Light can't come here. You can't ever talk to it. Which is to say that for every person in this universe, wherever you are in the universe, okay, around you there exists a sphere. And only the stuff within the sphere can you talk to and understand what's going on. And everything on the outside of the sphere forever will remain outside your sphere of influence. Outside, there's no way you can receive information and talk to what's going on there. And if I can leave you with one last, since all of you said you're interested in astrophysics and relativity and understanding space and gravity, you now know one last thing, which is that if I move to a frame of reference, it's given to me this way. This is my frame of reference. To someone else, their frame of reference would be the same, but I'd look different, right? I'd be somewhere there. What I wanted to tell you is that a discovery that was made, I think it was in the early 2000s, was that through all of space, there exists this radiation that's all around us. It's called the cosmic microwave background. I think you've all heard of it before, at least in your articles, right? There's this all-permeating radiation called the CMB. But here's what's interesting, that if you take a bit of CMB from here, and you take a bit of CMB from this part of the universe, here, or here, or here, or here, okay? There's no undo, is there? The point is, this is the speed of light, right? This CMB has the same temperature as this CMB, which means that for any objects to have the same temperature, they must have been in contact, exchanged heat, and then arrived at the same final temperature of 3 Kelvin, right? So this CMB here has the same temperature as the CMB here, but the idea is that then you can ask, how long ago were they in causal contact with each other to talk to each other, exchange heat? And what you find out is that if this is the Big Bang, okay, you needed a lot more time than the 14.8 billion years for these two different patches of the sky to be in contact with each other to talk. This is a fundamental problem in physics. It's one of the biggest unsolved problems in physics, which tells us that if you take any two stars, when you look at the CMB at the sky, they don't even have to be at other opposite ends of the universe. But even if they were separated by 1 degree, just 1 degree in the sky, okay, they're so far apart that for them to have been able to talk to each other, their light cones just do not reach, well, the Big Bang. You need a lot more time to explain how they were able to talk to each other. And this problem that I'm explaining to you is called the horizon problem. It tells you that two parts of the CMB were not within their, they needed to have traveled faster than the speed of light to have spoken to each other. I think that's a good place.
So that is where inflation comes around, right? The idea of inflation.
Inflation is one particular attempt at explaining this, but it's not conclusive. There are problems with inflation as well. But that's one answer. Any questions on today's session? Was this helpful?
It was like, to be honest, it was like this one good book that you keep and you just want to keep reading the book. Like it was.
I'd really like honest feedback, because if you think this was either too philosophical,